So we're working through the chapter that describes energy and introduces us to the first law of thermodynamics. And we've covered a lot of ground already, a review of mechanical energy, talk about kinetic potential, work, lifting a weight, rotating a shaft, electrical power, mechanical power, and then we noticed about the integral PdV, boundary work. So I have a gas, typically a gas, trapped in a piston cylinder apparatus. There's some boundary work associated with it. And last time I left off at polytropic process. Well, what is a polytropic process? Anything where I can get in a relationship where PV to any power, let's say n, a coefficient n, is equal to a constant. So for example, n could be 0. In that case, this equation reduces to, so if n is equal to 0, then p is equal to a constant, isn't it? And let's say I want to plot on a pressure volume diagram starting at state 1 with V1 and going to state 2, V2. What would a constant pressure process look like? It would look like that, wouldn't it? Very simple. All right. Let's do another case. If n is equal to 1, then I have P times V is equal to a constant. That's not a straight line, and you would have to be really good at recalling stuff from your math classes a long time ago. There's a name to that type of line where you have y is equal to a constant over x, or y times x is equal to a constant. Rational? That doesn't ring a bell with me. Anybody else? What type of shape does it have? It kind of asymptotes and asymptotes to the axes and curves like that. Depending on constant, the constant can push it out or pull it in. Hyperbolic. Yeah, that's the name that I remember. Hyperbolic. Don't worry, it's not on the quiz. All right. So what you'd have is you'd have something where it starts at maybe a P1 and V1 and goes to a lower pressure, P2, as it expands to a larger volume, V2. True? And then maybe if n is not equal to 1, maybe it's equal to 1.3. How do we get 1.3? Well, when we get into entropy and we get the ideal gases, and then we find it's about 1.4, okay, for a lot of cases. What does that equation look like? Well, PV to the 1.3 is equal to a constant. I don't know quite how to plot that, but I'll give you a question. Should this be a first clicker question? Let's make it a clicker question if you have your clickers with you. And compared to the other one where this curve right here, I plotted where this is PV to the 1 is equal to a constant. Do you think that the curve, if it starts at the same point, would come out lower or higher? Would PV to the 1.3 look closer to the answer A, select answer A, or closer to the answer B? And we start. So we change that coefficient n from 1 to 1.3. What does the line do? Does it go down further or go up a little bit? Answer A or answer B? All right, we got 24 people in. Let's take a look. Boom. Answer A is correct. And so it's kind of thinking about it. Where was the first one where it's n is 0? Isn't that the first case? Then this was the second case, and it's the trend going down to the third case. And so A was the correct answer. Very good. Now, I encourage you to read the textbook. Example 2.1 covered this. If you haven't already worked out example 2.1 and spent some time on it, you're behind the ball. Okay? All right, let's move on. Let's solve this problem. a gas within a piston cylinder assembly undergoes a process from a state where P1 is 30 kilopascal and V1 is 0.07 meter cubed to a state where P2 is 130 kilopascal and V2 is 0.014 meter cubed. The relationship between pressure and volume during the process is linear. So it's a linear relationship. Determine the work for the process. So what do I typically like to do is organize the information given. So we start at state 1, and we just repeat the information. P1 is 30 kilopascal. Is that a high pressure, low pressure? What type of pressure is that? It's a low pressure. It's a state of vacuum, actually. Is that absolute pressure, gauge pressure? When it's not explicitly said to be gauge, it's absolute. It's absolute. All right, so this volume 1 is 0.07 meter cubed. And then you go to state 2, so P2 is equal to 130 kilopascal. Let's describe 130 kilopascal. What's that? It's above atmospheric pressure. Atmospheric pressure is about 100 kilopascal. And then V2 is 0.014 meter cubed. What happened to the volume during the process? Did it enlarge, or did the volume get smaller? Smaller. So this is a compression process. As the gas volume gets smaller, what did the pressure do? Went up. Makes sense, right? Makes sense. So now what we'd like to do also is plot these things. Our favorite plot, pressure in kilopascal and volume in meter cubed. We have a value of 0.014 and we have a value of 0.07. If I double 0.014, it's not quite whatever. I forget the ratio. If you have a calculator, what is that ratio? I didn't bring a calculator, and I didn't calculate that ratio. But it's compressed a lot, and maybe I don't think I've drawn it to scale. But sometimes it's helpful to draw it to scale. Then maybe down here we'll put 30, and then we'll put 130. And then where do we start? We start at 30 at the larger volume, don't we? Isn't that where state 1 is? And we end at the smaller volume at the higher pressure. Isn't that state 2? And what does the line on a PV diagram? They said it's linear. It's a linear relationship. So isn't that the line? And it goes from 1 to 2. Now, I think I've organized the work a lot. Now we look at the problem statement and says, determine the work for the process. I'm looking to calculate something. What symbol should I use for the something I'm asked to calculate? W, cap W, right? So let's find W. It's the work for the process. This is a boundary work. You could put WB. You don't have to. W is good enough for me, but it's a boundary work. How would I calculate it? Well, first of all, what units? Well, I'm looking for W in units of kilojoule because they even tell me, give it to me in kilojoule. What principle am I going to use to calculate that boundary work? The area under the curve, but let's do this one. Let's just be a good mathematician and say the work is the integral P dV. True? And so if the integral P dV, I need P as a function of V. This I really encourage you to do. I think it helps rebuild your knowledge about linear interpolation. A lot of people can't I got 2 points. Can I get the equation for a straight line through it? Ooh, cobwebs. Been a while since I've done that. But we should be able to do that. We should be able to get an equation like y is equal to mx plus b, a straight line. Where in this case, y, the y-axis is pressure, x, the x-axis is volume. What's m? The slope, and b, the y-intercept. True? So you could do it your own way, but you got to get it right. But one way I would do it is something like this. I would say, okay, P minus P1 divided by P2 minus P1 is equal to V minus V1 over V2 minus V1. It's kind of a linear interpolation. And so I can use this equation. I remember that from way back when. And I can stick in any V, and I'll get the correct P. You remember an equation like this? Maybe? Yeah. And so we can then manipulate this equation. So P is equal to, and then you're going to get minus V1 times P2 minus P1 divided by V2 minus V1. Now I got to clean this up a little bit. Put V minus V1 there. And then we'll put plus P1. And then if you wanted to, you can manipulate a little more, and you get V times P2 minus P1 divided by V2 minus V1. And then I'll put plus P1 minus that V1, P2 minus P1 over V2 minus V1. So this is my intercept. This is my slope. This is the x-axis. V is volume is on the x-axis, and P, the pressure, is on the y-axis. And so if I did this correctly, I'm going to talk a little bit right here. I'll get P is equal to negative 17855.7143 V plus 155. No matter how I encourage students to go back and review fundamentals of significant figures and other stuff, there's always a handful that just don't think through the process. And so what I'll be doing is I'll be grading a final exam in the second thermodynamics class. And some student will go an intermediate calculation. They'll say, oh, P is equal. He told me 3 significant digits. I'm going to give them 3 or less. They sometimes give me less on an intermediate step. That calculator showed all those, but they'll say negative 1790 V plus 155. Do you want to do that? That's rounding off. You're going to lead a bunch of round off error, and away you go. Your final answer will be drifted off. And some problems are very sensitive to more round off error, and some are less sensitive. So what do? I get this question every semester. Keep all the digits on intermediate calculations. And then at the very end, round off to 3. All right? I'm kind of being a little defensive here because I know the first test I'll grade and I'll throw back and it'll be like people lose points. It's like, I tried to warn you. I'm doing that right now. So you don't have to keep 18. If your calculator keeps 7, 9, 18, fine. Keep them all. No problem. Your calculator's not going to break out in a big sweat. If you do need to round it off to at least 5. Round off to 6. That way you don't drop any. Okay? So what I could do is I'd say negative 185.71. And then that's V plus 1.55, not 155. Now that I have an analytic expression, I just stick it into the equation, so the work is equal to the integral of negative 1785.71 V plus 155. We're going to integrate that with respect to V going from the lower limit. The lower limit. Where do we start? Do we start at V1 equal to 0.07 and end at V2, which is 0.014? Or not? Or does it matter? Switch the limits. We can just switch the limits. If you switch the limits, what happens? Think about it mathematically. What happens if you switch the limits? If you put, oh, I'm gonna integrate from 0.014 to 0.07. What'll happen to your answer? It'll be the wrong by the sign. The sign will be wrong. Do that. Don't trust me just by that. Check it out yourself. You'll get a negative answer. Okay? So we want to start from the lower limit, V1, which is 0.07. But Professor, that's the larger volume. That's right. It's right. You're integrating backwards. The mathematicians never taught you that, did they? You always integrated from x1 to x2, and x1 was always less than x2. But that's not the way it has to be. And so 0.014, the smaller volume, is the final volume. And so you'll pick up negative 1785.71, 1/2 V squared, evaluated 0.07, 0.014, plus 155 V, evaluated 0.07, 0.014. I'm belaboring this a little bit, am I not? But you don't want any errors. And so what we find is we calculate something like 4.2 minus 8.68. I usually do it in multiple steps if I'm a little uncertain. Then I can rerun my calculator. How many people take tests and given time, they run everything at least twice on their calculator during an exam?
3 times.
3 times is the right answer if you've got time. Why throw away points? I've taught statics before, a lot of times. And I'll give them a test, and it's so doable. But I want to be doable within 50 minutes, right? And then there'll be, I don't know what it was, but it'd be like a contest. The flame down, there it is, 15 minutes into the exam. I'm done. And they go out. Hello, friends, bye-bye. You're still working, and I'm done. And then there'll be another one, 20 minutes and 25 minutes. And it's like you pick it up, you just got to look at it when you're grading it. You say, why did that student think it's more fun to leave this room instead of check their work? And they got a C when they could have easily gotten an A. Don't do it. I'm kind of helping you here. You may not like this type of lecture, but I've got to try and do that because unfortunately some people are going to be shocked when they don't pass this class. Also, I didn't chase my units on this, did I? Let's go ahead and take a look at our units. You've got to chase, what are the units on this pressure? I forgot to do that. That is in kilopascal. What are the units on this 155? That's kilopascal. What are the units on this negative 1785.71? That's kilopascal per meter cubed, isn't it? Because V is in meter cubed, V is in meter cubed. So that constant does have units right there, and that constant has units. And when you come down here, you could see that it's going to be kilopascal times meter cubed. Kilopascal times meter cubed. It goes right to kilojoule. You've got to work it out yourself. Should I work it out with you or not? Who wants to see it worked out? Go for it. All right, I need more room. But you need to do this. Make sure you're confident in it. So a kilopascal times a meter cubed. I want to know what that is. So I say kilopascal times a meter cubed. Did I make an error yet? Is this equation correct? The equation is correct. Restrain yourself to manipulate only the right-hand side. So Pascal is a Newton per meter squared, true or false? Did I just multiply this right-hand side by 1? I'm good to go. Is this good? And so the pascals can go, right? Okay. Leave the kilo. The kilo did not go away. All right. Now, can I get rid of meter squared? And then what is a joule? Is it a Newton times a meter from your memory? It sure is. And so the meter goes, the final meter, the newtons go. I'm left with 1 kilojoule. 1 kilopascal times a meter cubed is 1 kilojoule. I'll use it a lot throughout this semester. So unit conversion, it's pretty fast then. And so this right away turns into the kilojoule, and you could check these units right here. The same thing will happen. You'll have that, let me just kind of show it, a kilopascal per meter cubed, but then you multiply by meter cubed times meter cubed because it's V squared. And there you go, it's kilojoules. So this work, the final answer is negative 4.48 kilojoules. Professor, what happens if we leave that negative sign off? You lose some points. What happens if I leave the units off? You lose some points. What happens if I put 18 digits in here, 9 or 6? You lose some points. What happens if I don't have an equal sign? You lose some points. What if I don't W over? You lose some points. You've got to get it just like that. Got it? All right, you had a question?
What was the negative again?
What is the negative?
Why is it negative?
Good question, because who's doing the work? Is the trapped gas receiving work by being compressed from the surroundings? Usually the face of the piston is a part of the surroundings and it's compressing the gas. That's what's happening. So the system is getting energy transferred into it via a work transfer by being compressed. And it's not going out. So our system is if W is positive, the traditional sign convention, it's work out. If work is negative, it's work in. The system's receiving that energy transfer. Now, somebody suggested let's do it graphically. You're the engineer. We just basically played mathematician for a while. Because this is why engineers love to plot things. So you can see, if you said get the area under the curve, that would be pretty easy to do for this problem, wouldn't it? So what's the area under the curve? It's a straight line curve. It's a triangle, so you just get the average. It's kind of like I can cut conceptually right here and take this part and flip it over and put there. And so graphically, the work is just the average pressure, AVG. I'm trying to get average pressure times the volume change. And then you look and say, oh, it's going compressing. I better make sure and get a negative sign on it. So with the graphical approach, you have to apply the negative sign. Mathematical approach, it falls out. But it would be 130 plus 30 divided by 2. So 160 divided by 2. Did I do that right? What is that, 80? So it's 80 kilopascal times well, you could do it where the change in volume, it's the final volume, 0.014 minus 0.07 meter cubed. Hence, you'll get the right sign. It'll come out with the negative. But a lot of times you just look at it, oh, it's just give me the difference, the larger minus the smaller. But this will work. And so what do you get for the graphical approach? Same answer. Negative 4.48 kilojoules. Professor, do I have to do it the mathematical approach? Can I do it the graphical? Unless I tell you what approach to use, you're on your own on the open-ended problems. Okay? All right. Now there's another mechanism for energy transfer. It's called heat. So heat is energy transfer when you have a temperature difference. Without a temperature difference, there's no heat transfer. By definition, you must have a temperature difference. There's conduction heat transfer. Think about it where you have a wall or a slab. On one side of the wall, there's temperature plotted there. It's high temperature, TH or something. On the other side, it's TC. Temperature profile is linear. You're going to have the flow of heat, Q, is equal to a K area change in temperature over the length. This would be some length like that. And this is a rate of heat transfer. So there's a Q dot. This is a property, thermal conductivity. I kind of just didn't put into differential form Fourier's law that describes heat conduction, but I said, look at the temperature difference across the slab of thickness L drives the heat transfer through that cross-sectional area. That wall has some area. Now, we're not going to use this equation much, especially beyond this chapter. There may be one or two homework problems or something. But we have a whole class, when you get to it, 4313 in the curriculum, required mechanical engineering majors, called heat transfer. So we beat you up on that one. Same with convection. Think about a surface that is warm. All of this is a solid, and it's all at temperature Ts. You pass a fluid over it. Maybe there's a fan. Maybe there's water. I don't know, something promoting the fluid flow over it. So you have bulk fluid motion, and that fluid's at a different temperature, and we usually put T infinity, meaning kind of far away from the solid surface. It's the fluid temperature close to the solid surface. It actually goes to TS. It's in good thermal contact with the solid, but far away it's T infinity. And then we have an equation that says, the rate of heat transfer from the hotter solid into the cooler fluid is the convection coefficient, the area, and then the temperature difference that drives that's a T infinity heat transfer. And this is our convection, I'll just say heat transfer coefficient, or just H. Okay. Radiation. Let's say I have the top of a building and I'm interested in the radiation off of the top of the building, that's my area of interest, to the sky which is cold. So I have some temperature for the sky, temperature 2. I have temperature for the top of the building, T1, okay? And this rate of heat transfer is given by Q dot is equal to an emissivity of the top of the plate. That's a property of the top of the building or top of the plate or something like that. I'm calling it plate or building. That's an emissivity times the area of the top of the plate or top of the building times a Stefan-Boltzmann constant. It's like pi. It's just a constant, but it has units. It's not dimensionless. It's Stefan-Boltzmann constant times temperature 1 to the 4th power minus temperature 2 to the 4th power. That's very interesting. There's very few things in engineering where you have something to the 4th power. Thermal radiation, that's what it is. So when things get hot, they transmit a lot of thermal radiation. When things drop in temperature, it really drops dramatically the amount of thermal radiation exchanged. Okay? You ever see something when it gets really, really, really hot, like a burner on a stove? What happens to its color? Electric burner on a stove starts to turn red. It's getting so hot that electromagnetic emission starts to bleed into the visible spectrum, and now your eyes can actually see it. If you take the burner in the stove that's cold, and then you have a room, curtains are all drawn, you turn the lights out, and you look at the burner in the stove, you can't see anything, it's all black. It's all black. You turn the lights on, what are you seeing? Photons that are bouncing off of the burner on the stove to let you see, there's the burner on the stove. You turn the burner on the stove on, it's now getting really, really hot. It's glowing red. You go over and you turn the light switch off. Can you see the burner on the stove? It's glowing red. It's coming from emission. Normally we see things from reflection, not from emission. They got to be really hot to see it from emission. And always, when you're itty bitty or something, it's like glowing red. It's like, I just want to touch it because it looks so cool. Right? How many little children reach toward a hot stove and want to touch it just because it's like, this is so unique that it's glowing red. Anyway, heat transfer, radiation, conduction, convection are all great topics. I'd love to teach that class when I get the chance to teach it. But this is a surface emissivity. And most surfaces are close to 1, being good emitters, but then you have shiny, metallic, silvery type surfaces, and that engineers purpose to have those because they have low emissivity, hence low exchange of radiation. Okay, well that's our introduction. What drives heat transfer? Temperature difference. Did you know historically in science and engineering there was this great divide? They thought work completely different than heat. They didn't recognize that energy is energy. It's just in a different form. This man came along, American-born English physicist. Benjamin Thompson was his born name. He fled Boston in 1776. He was basically with 1/3 of the Americans at the time. He was sympathetic to the crown. Boston fell. They got on a ship and left. They went to England. He was part of that group. He actually left a wife and a lot of property and in America at the time. And then he lived in did a lot of work, Poland and other places, Holy Roman Empire. That's where he got the Count Rumford, his designation for his contributions. One of the less significant contributions, but one of the things we recognize him in thermodynamics for, is that he was in charge of boring cannons for the Holy Roman Empire. And this is just a kind of comic strip illustration, but you get a bunch of horses and you get a lot of mechanical power through some gearing mechanism, and you bore out, after you cast a solid chunk for your cannon, you got to bore it out, take all that metal out of the middle. And that was very big deal at that time in making. And what he found was those chips come out hot. These little metal chips are very, very hot. And he's thinking, the theory says heat is different than work, and there's this caloric theory for heat transfer, and it's some sort of fluid, and you treat it like that. But he even wrote a paper on his observations. Heat is a form of motion. He's linking them together. An experiment in cannon boring, and that was done in 1798. This is a replica of that cannon boring. I think they had horses below that went in a circle, mechanism to bring it up, and then the cannon actually, I think, turned, and the bore stayed stationary, and the operator was very high-paid, high-skilled job at the time. So almost 1800. And you can read, I think it's worth reading. Let me kind of read this to you. By meditating on the results, he just reflects on it. All these experiments, we are naturally brought to the great question which has so often been the subject of speculation among the philosophers, namely the question, what is heat? Is there any such thing as an igneous fluid? Igneous, on the next page I have, you just go to Google and say, what does that word mean? Rare use of the word meaning fire or fiery. That's his use of the word, igneous. Otherwise, it means volcanic type of rock, igneous rock. Is there anything that can, with propriety, be called caloric? Caloric. That was the common term at the time, caloric. And so caloric, you look it up, historical noun, in the late 17th and early 19th centuries, a hypothetical fluid, substance, that was thought to be responsible for the phenomenon of heat. They thought that some fluid was being transferred when you had transfer of heat. They called it caloric, some fluid that's fiery that you can't really see. But his cannon boring machine, he would put a dull bit in there, and he could turn it, and through the friction, he could boil all the water he wanted all day long. And that marveled people and marveled him. And that went contrary to the caloric theory. It's kind of like once it's transferred, it's done. Here he's like transferring. So it's hardly necessary to add anything which an insulated body or system of bodies can continue to furnish without limitation. Like he could bore that cannon all day with a dull bit, make a lot of friction, a lot of heat. Without possibly any material substance, it appears to me to be extremely difficult, if not quite impossible, to form any distinct ideas of anything capable of being excited and communicated in the manner the heat was excited and communicated in these, except it be motion. That was nice work transfer coming in. And it was just being dissipated through friction. All of that energy realized by heat, making things hot. Today you say, kind of boring. At the time, earth-shaking. What he didn't do was he didn't make good measurements of the equivalence of heat and work. And then, take a look at the year, almost 1800, right? This man, James Prescott Joule. Have you seen that name before, or that word? We honor him by that unit, kilojoule or joule, amount of work. He did a paddle wheel experiment. What year did Rumford do his cannon experiments? What's the difference? 40-some years later? 47 years later. That's a long time. People are still struggling with this. And he published about the mechanical equivalence of heat. So it hadn't been settled, but this pretty well settled it. And this is a picture, I think, of the equipment. And you can take a look. I didn't double check it, but basically you have a mechanism with the string, and you bring it over to some weights, and you let the weights fall, which pull this and turn it. And inside you have water and paddle wheels, and so it's just going to beat that and churn that water. It's going to dissipate all that mechanical energy through viscous dissipation and make the water warm. That's what he's trying to do. Some of them are stationary, and you put that into a nice insulated container where they had made good measurements on heat transfer. They knew the specific heats of fluids very well, and so they could measure temperature very well, and they would watch it heat up. And you could say how much work was done by dropping that mass in a gravitational field, and how much heat was realized by increasing the temperature of the water inside in the mass of the container. And so this is it. He had a ruler. He watches the weight drop. He has it connected. He has a thermometer. He's watching that paddle wheel churn up the water, and he's seeing that water increases in temperature. The only way before the water would increase in temperature is a transfer of caloric, some fiery fluid substance due to the temperature increase. Was there any temperature difference to drive that heat transfer? No, there was no heat transfer to warm it up. So he concluded from his experiments and very careful observations that 4.15 kilojoules of mechanical energy is equivalent to 1 kilocalorie of heat transfer. Different units they were using, which today we would say, oh, the specific heat of water is 4.15 kilojoules per kilogram degrees C. Subsequent experiments many times repeated, they get a better answer, 4.186 kilojoules per kilocalorie, or you interpret it as the specific heat of water about 4.186 kilojoules per kilogram degrees C at room temperature. So mechanical work did raise the temperature of the fluid. There is a mechanical equivalence between heat. So we came up with this energy balance. It's the first law of thermodynamics. We write it for a process starting from state 1 to state 2. So we say, the energy of the system can change. It can change by having a heat transfer in, or it can change by having a work transfer out. That's the simple form. You say, well, this energy, this cap E is the total energy of the system. You could say, well, it's made up of 3 ways it's represented in this class. We're going to talk about the change in internal energy, the change in kinetic energy, and the change in potential energy of the system. So before they had the mechanical equivalence of heat, it was just this equal to that. Okay? That was just like the conservation of mechanical energy. But now you bring in the heat transfer and you bring in a change in internal energy. So what is this term? We understand kinetic, we understand potential, we understand work. What is this change in U? It's in the change in internal energy. It's associated basically with the temperature and pressure of the system. That's about it, what we could say. How about this Q? Well, we just described conduction, convection, radiation, but other than that, for this class, most of the time we don't predict it from Fourier's law or Newton's law of cooling or Stefan Boltzmann law. We just say, here it is, or you have to calculate it using an energy balance. Work, we can do a pretty good job of either calculating it from the energy balance or going back to integral F. This work, integral F dx, integral P dV, or integral tau d theta, right? Or even you could do the electrical, the integral with respect to time of the W dot electrical will allow you. There's a couple ways to get the work, okay? But not that many ways to get the heat transfer. And the new term is that internal energy, which is primarily a function of temperature and maybe another intensive property like pressure and mass. So we have these forms. The forms of the energy. Kinetic energy would be 1/2 mv squared. If you wanted to, you could talk about the specific kinetic energy. That would be 1/2 V squared. That would be how much energy per unit mass. You have potential energy, mgz, or on a specific per unit mass basis, gz. Internal energy, cap U. Lowercase u on a per unit mass basis. Lowercase u is equal to cap u divided by m, the amount of mass. Transfer of energy, we have the work, W. Number of ways to calculate it. Heat, well, fewer ways, but the idea is the same. You could calculate it if you had that class heat transfer already. And then the specific work per unit mass is lowercase w, and the rate of the amount of heat transfer in the process per unit mass is lowercase q. All right. We have three ways we can write an energy balance. We showed it for a process from initial state 1 to final state 2. Change in internal, change in kinetic, change in potential energy equal to Q minus W. If you want to put it on a per unit mass basis, change in lowercase u plus change in lowercase ke plus change in lowercase pe equal to Q lowercase minus W lowercase. Each term here is in units of kilojoule. Each term here is units of kilojoule per kilogram or something like that. A differential form would be where you say, okay, a small change in U, a small change in the kinetic energy, a small change in the potential energy is equal to a small amount of heat transfer or a small amount of work transfer. That's infinitesimally small process or change. And then if you wanted to, you get to the rate equation by taking this equation, multiplying by 1 over delta T. And so what we get is the rate of change of internal energy, you could put it on a mass basis or whatever, plus the rate of change of kinetic energy, plus the rate of change of potential energy is equal to the rate at which heat is being transferred in minus the rate at which work is being transferred out. Now, it's good to know these equations, but you really have to apply them and solve a lot of problems. Next time we'll talk about a cycle. All right? Thank you for your attention.